Chapter 17 Development of the Human Eye. Page number 624. Development of cornea. Primary corneal stroma. The development of the cornea is triggered by the separation of the lens vesicle from the surface ectoderm at 33rd days of gestation. At this stage, the ectoderm consists of two layers of epithelial cells that rest on a thin basal lamina. Studies in developing chick embryos have shown that detachment of the lens vesicle induces the basal layer of epithelial cells to secrete collagen fibrils and glycosaminoglycans to fill the space between the lens and the corneal epithelium. The extracellular matrix molecules constitute the primary corneal stroma, which contains only macrophages that engulf the debris remaining after detachment of the lens vesicle. In the human embryo, however, the primary stroma is poorly organized and consists of fine filaments, amorphous material, and only a few collagen fibrils. Mesenchymal cells derived from neural crest, which migrate into the developing eye beneath the basal lamina of the corneal epithelium and form the posterior surface of the primary stroma and the fibronectin containing basal lamina of the anterior lens cells as the substrate for their migration. This event marks the first of three successive waves of ingrowth of neural crest cells into the developing anterior segment of the eye. Corneal epithelium. In the 17-18 mm stage of embryo, that is about 40 days of gestation, the cornea consists of a superficial squamous cell layer and a basal cuboidal epithelial cell layer, a primary stroma, and a double layer of flattened endothelial cells posteriorly. Scanning electron microscopy shows that by the 7th week of gestation, the superficial layer of epithelial cells is pentagonal or hexagonal in shape with a maximal diameter of 10 to 20 micrometer. Microvilla and fine microplici are already present on the anterior surface. Ultrastructurally, these cells are electron dense, flat, and contain many glycogen granules. Very rarely, desmosomes connect the superficial cells with the underlying cuboidal cells. Between the 2nd and 3rd months of gestation, most of the superficial cells increase in diameter to 15 to 20 micrometer and are covered by microvilla and fine microplici that are distributed homogeneously over the cell surface. These cells are more electron-lucent than previously and do not have as much glycogen. A large number of desmosomes now connect this cell layer with the underlying cells. Beginning at the 4th month, 3 types of superficial cells can be distinguished. Small cells with the largest number of microvilli or microplici, medium-sized cells with intermediate numbers of surface projections, and large cells with the fewest microvilla and microplici. Obviously, microvilla and microplici are to increase the surface area, and that's why the large cells are, we can remember it as large cells having the fewest microvilla and microplici. These large cells are of desquamation. Thus, the surface morphology of the human corneal epithelium attains an almost adult appearance by the time the eyelids open at 5th to 6th months of gestational age. Stroma. Further development of the corneal stroma is preceded by the growth of another wave of mesenchymal cells from the rim of the optic cup. This proceeds in 2 directions. At about the 19 mm stage embryo, the cells of the posterior extension grow into the space between the lens epithelium and corneal endothelium and are destined to form the primary pupillary membrane. At about the same time, the extracellular matrix of the primary stroma swells, apparently as a result of hydration of hyaluronic acid to make space available for the next migratory wave of cells, that is, third wave of the neural crest cells. At approximately 7 weeks of gestation, when the embryo length is around 22 to 24 mm, the anterior extension of mesenchymal cells migrates between the corneal epithelium and endothelium and will contribute to the further development of the corneal stroma. The central region of the stroma is initially acellular. The ingrowing cells differentiate into stromal fibroblasts or keratocytes that will actively secrete the type 1 collagen fibrils and the matrix of the mature, that is secondary corneal stroma. Initially, the secondary stroma is rich in fibronectin, but this disappears as the mesenchymal cells come to occupy the entire region. The stroma soon attains its maximum width, which is approximately double the normal post-embryonic width. This decreases because of dehydration, especially of hyaluronic acid, and compression of the connective tissue. The stellate mesenchymal cells that are dispersed randomly in the stroma gradually change into spindle-shaped cells that are oriented parallel to the corneal surface. This morphogenesis begins posteriorly in the cornea and is followed rapidly by the appearance of collagen fibrils. However, glycosaminoglycans rich in carboxyl and sulfate residues are synthesized before the formation of collagen fibrils. Keratin sulfate is not detected until 6 months of gestational age. The collagen fibrils are organized as lamellae, each of which continues to grow by the formation of additional fibrils, that is interstitial growth. At the same time, successive layers of lamellae are formed, appositional growth. Because the lamellae increase in length as well as in width, the diameter and the thickness of the cornea increases. Centrally, the corneal stroma of an 8-week-old human embryo at the stage of 30 mm length consists of 5 to 8 rows of cells. The most posterior layers of the stroma are confluent at the periphery with the condensed mesenchymal tissue of the future sclera. The number of stromal cell layers increases rapidly, and by the 35 mm length embryo stage, the cornea consists of 2 layers of epithelial cells, a stroma with 15 layers of cells and scant collagen fibrils, and an endothelium that is still arranged as a double layer of cells. Descemet's membrane and endothelium. By the 3rd month, embryo length 63 mm, the endothelium in the central region of the cornea has become a single layer of flattened cells that rest on their interrupted basal lamina, that is, the future Descemet's membrane. At this stage of development, the basal lamina is composed of an electron-lucent zone, lamina lucida, 37.5 nm thick, adjacent to the endothelial cell layer, and an electron-dense band, lamina densa, 36.7 nm thick, towards the corneal stroma. Further differentiation and growth of Descemet's membrane are accomplished by the subsequential secretion of a series of individual membrane units to form a multilayered structure. The process takes place rapidly because, although only one such layer is discernible at 12 weeks of gestation, approximately 10 layers are present by the 6th month and 30 to 40 layers at birth. At the same time, as the deposition of membrane units is occurring, short thin linear filaments about 170 nm long and 40 nm in diameter are laid down perpendicular to and between adjacent layers. It is suggested that these filaments function as cross-linking bridges which bind and pull together the adjacent membrane unit layers and, during the last trimester of gestation, cause compaction of this region of desmus membrane. Transmission electron microscopy of flat sections of this region of desmus membrane reveals that the fibrils are arranged in a hexagonal fashion and interconnected with nodes and internodes of electron-dense material, thus producing a lamellar pattern of equilateral triangles with size of about 110 nanometer. Because of its unique organization, this anterior third of desmus membrane is recognized as the fetal banded zone and attains a maximum thickness of about 3 micrometer at birth. In postnatal life, a homogeneous fibrilo-granular material, the so-called posterior non-banded zone, constitutes desmus membrane which continues to thicken with age. The apices of the endothelial cells are joined by zonula occludentis in the middle of the 4th month, which corresponds to the onset of production of aqueous humor by the ciliary processes, and the middle layer of wing cells in the epithelium develop. At the 6th month of gestation, desmus membrane is demarcated clearly, and the stroma consists of an immature extracellular matrix that includes collagen fibrils and numerous active keratocytes. Bowman's zone. Bowman's zone of the anterior stroma is not formed until late in the 4th month of gestation. This region is always acellular. It is presumed that the most superficial keratocytes synthesize and lay down the ground substance and collagen fibrils as they migrate posteriorly to the stroma. What contribution, if any, is made by the primitive epithelium to the development of Bowman's zone is unknown. At this stage of development, 17 to 18 weeks gestation, the basal lamina of the corneal epithelium consists of a relatively thin lamina lucida, average thickness 41.68 nanometer, and a fully developed lamina densa. Hemidesmosomes and anchoring filaments are developed only partially. The filaments' average length 474 nanometer and diameter 17.6 nanometer arise at the basal surface of the epithelial cells, traverse the lamina densa and lucida, and terminates in Bowman's layer. By 26 weeks of gestation, the anchoring filaments with the typical adult appearance are present, especially at the site of hemidesmosomes. At birth, the filaments and fibrils are already intermingled with the fully developed collagenous tissue of Bowman's layer. The diameter of the unfixed human cornea increases from 2 mm at 12 weeks gestation to 3.5 mm at 15 weeks, 4.5 mm at 17 weeks, 5.5 mm at 21 weeks, and 9.3 mm at 35 weeks. Once the adult size is attained, the turnover and replacement of collagen fibrils is normally extremely slow. Figure 17.9. Diagrammatic representation of the 3 successive waves of ingrowth of neural crest cells associated with differentiation of the anterior chamber. 1. First wave forms corneal endothelium. Second wave forms iris and pupillary membrane. Third wave forms keratocytes. Figure 17.10. Diagrammatic representation of development of central cornea. At 39 days gestation, a 2-layered epithelium rests on its basal lamina and is separated from the endothelium, which consists of 2 to 3 layers of cells, by a narrow space. At 7 weeks, figure B, mesenchymal cells at the periphery migrate between the epithelium and endothelium. C. By 7.5 weeks, the mesenchymal cells, future keratocytes, are arranged as 4 to 5 incomplete layers and a few collagen fibrils are present. D. By third month of gestation, the epithelium consists of 2 to 3 layers of cells. The stoma has 25 to 30 layers of keratocytes that are arranged more regularly in the posterior half, and a thin, uneven Descemet's membrane is present between the most posterior keratocytes and the now monolayered endothelium. Figure 17.11. Scanning electron micrograph of the anterior surface of the corneal epithelium at the 7th week of gestation. Most cells are covered with fine microvilli and microplici. A. And a few have coarse microvilli. Error. Scale bar equals to 10 micrometer. Figure 17.12. Stages in development of Descemet's membrane as seen by transmission electron microscopy. In each micrograph, the stroma is above, the corneal endothelium is below. Figure 17.12. Stages in development of Descemet's membrane as seen by transmission electron microscopy. In each micrograph, the stroma is above, the corneal endothelium is below, and Descemet's membrane is demarcated by arrowheads. Original magnification 20,750 times. A. In the 12-week-old fetus, Descemet's membrane is thin and continuous and consists of an electron-dense layer adjacent to the stroma and an electron-lucent layer next to the endothelium. B. Approximately 3 electron-dense layers, each separated by an electron-lucent area, are present in the 16-week-old fetus. C. By 19 weeks of gestation, the number of lamellae has increased to 5. Narrow interlamellar zones are cross-linked by thin linear filaments arrow, whereas wide zones are devoid of such structures, double arrows. Figure D. At 26 weeks of gestation, Descemet's membrane consists of approximately 10 layers with many cross-linking filaments. Figure 17.13. Stages of development of the basal lamina of the corneal epithelium as revealed by transmission electron microscopy. Original magnification 25,000 times. Figure A. At 18 weeks of gestation, the basal lamina consists of a thin lamina lucida (LL) and a fully developed lamina densa (LD). Anchoring filaments AF and hemidesmosomes HD are also developed. BL stands for Bowman's layer. Figure B. In the 26th week old fetus, the number of anchoring filaments AF shown at high magnification 35,000 times. In figure C, has increased and more collagen fibrils are present in Bowman's layer BL. Figure D, at 1 year after birth, the lamina densa is thicker than the fetal cornea and densely packed collagen fibrils are present in Bowman's layer. Thank you.